In today's lecture, we will talk about nanotechniques in proteomics. In the last few lectures, we talked about different type of label-free technologies such as SPR, SPRI, ellipsometry, interferometry and the different kind of platforms. Today, we will talk about different type of nanotechniques, how they can be used for various types of proteomic applications. We will discuss more on their applications, discuss their advantages and disadvantages and compare each of these methods with others, and then we will touch upon how these nanotechniques can be applied for proteomics based applications. We will learn about some of the nanotechniques which are applied for proteomic applications. The nanotechniques offer several advantages over the conventional proteomic methodologies such as miniaturization of assays, real-time multiplexing capability, low sample and reagent consumption, very high sensitivity and faster assay time. There are several nanotechniques such as carbon nanotubes and nanowires, quantum dots, gold nanoparticles, silicon nanowire field effect transistors, which are now increasingly being used for various proteomic applications. These applications include biomarker discovery, immunoassays and different types of biomolecular interaction studies, including protein-protein interactions. Successful integration of nanotechnologies with proteomics has now introduced a new field in the clinical research known as nanoproteomics. This is one of the very rapidly emerging areas for the biomedical research, which may ultimately have tremendous therapeutic potential. In today's lecture, we will talk about different nanotechniques used for proteomic applications. We will talk about carbon nanotubes, nanowires, carbon nanotube field effect transistors, CNT FETs, quantum dots, QDs, gold nanoparticles and nanocages and microfluidics. Let us first talk about carbon nanotubes and nanowires. There are various novel inorganic nanomaterials which have been explored in biological research with an intention of developing new types of analytical tools. Due to the rapid advances in synthesis and surface chemistry optimization, there are various classes of nanostructures including nanowires, nanotubes and nanocrystals that have been used for the clinical proteomics research. CNTs or CNWs, carbon nanotubes or nanowires, they detect changes in the electrical conductance after target binds and they show sensitivity in nanomolar to picomolar range. So, what are CNTs? These are hollow cylindrical graphite sheets which show high chemical stability and mechanical strength. The carbon nanotubes and nanowires offer very unique electrical, thermal as well as spectroscopic properties. And these unique features of carbon nanotubes and nanowires have opened up many new perspectives in the field of nanoproteomics. There are two different types of carbon nanotubes, single walled nanotubes SWNT and multi walled nanotubes MWNT. The single walled nanotubes are composed of a single graphite layer with the diameter in the range of 0.5 to 2 nanometer, whereas the multi-walled nanotubes are composed of several concentrically arranged cylindrical layers. There are various properties associated with each of this group, but today we will focus more on how these nanotubes can be applied for proteomic applications. The single walled nanotube possesses well defined electrical and mechanical properties which makes them promising candidate as a biosensor. The applications of single walled nanotubes in proteomics relies on the conductance change. Binding of the target protein to the functionalized device brings a change in the electrical conductance that is measured for monitoring the binding interactions. These carbon nanoparticles have various properties, and some of these general properties are listed here. They have a very high potential for signal amplification. They have a fast electron transfer capability, exhibit very high surface area to weight ratio. They can selectively bind to biomolecules after functionalization, and a selective binding with high sensitivity is the key advantage of using these nanotechniques. They exhibit high chemical stability and mechanical strength as discussed earlier, and these changes in conductance due to the binding of charged macromolecules can be measured for monitoring binding reactions. The slide shows the image for carbon nanotubes with functionalized antibody. The image on the top represents the unbound state, where you have a source electrode and a drain electrode. Some target proteins are observed to be binding in the bottom image, showing a change in conductance displayed in the graph on the right. The binding of the target protein to the functionalized carbon nanowires lead to a detectable change in electrical conductance, and this change in conductance is measured for detecting different types of proteins as well as small particles, including viruses. There are various applications showing the potential of this technology. Let us discuss some merits and demerits of using carbon nanotubes and nanowires. They allow real-time analysis similar to the some of the previously discussed label-free techniques, including SPR, where we had the opportunity to monitor the reaction in real time, which is not the case with the label-based techniques, which are mostly endpoint analysis. The approach also provides the multiplexing capability and offers miniaturization. There are also various demerits associated with this approach. Firstly, the metallic impurities can reduce activity of these assays. It is not very easy to determine how pure these preparations are. So, the degree of purity is one of the limitations here. One of the major constraints is their insolubility in biologically compatible buffers, since they are not compatible in all biological buffers. To demonstrate the principle of carbon nanotubes and nanowires, let us look at this animation. Carbon nanotubes. The carbon nanotubes are hollow cylindrical graphite sheets that exhibit very high levels of chemical and mechanical stability. As you have seen here, there is a drain electrode, source electrode, and on top of the carbon nanotube, the antibodies are functionalized. So, these nanotubes can be suitably functionalized with the antibodies or other agents like aptamers. The antibody coated nanotubes show no variation in conductance when they are in the unbound state. Binding of target protein to the antibody is detected by a change in conductance of the carbon nanotube with time. As you can see in the right panel, the time axis on the x axis and conductance is plotted on the y axis, which is showing a change in the conductance due to the binding state of these target proteins. These nanotube devices have been extremely useful for real time label free detection of low abundance proteins, and its sensitivity ranges from nanomolar to picomolar range. Now, after looking at the principle of nanotubes, let us briefly discuss about its applications. The carbon nanotubes and nanowires have shown unlimited potential for various applications in different fields. However, here our discussion will be centered on applications in context of proteomics. So, various types of clinical studies have been performed using nanotubes and nanowires to test the potential of these nanotechniques for cancer biomarker detection or to immune disease detection, direct assaying of human serum, deactivation of toxins and biological detection and imaging. This is a very small list of the unlimited applications which have been demonstrated by using carbon nanotubes and nanowires. Let us now move on to another platform, which is carbon nanotubes field effect transistors CNT FETs. The successful combination of carbon nanotubes with field effect transistors has led to the development of this novel sensing device known as CNT FET. As we have discussed, there are different types of carbon nanotubes, SWNTs and MWNTs. The single walled nanotubes exhibit semiconductor properties which are optimal to design the CNT based electrical sensors. The functionalization of carbon nanotube field effector transistor with a specific receptor brings about binding of the desired target biomolecules. For example, we can immobilize surface with a specific receptor antibody and then target proteins can be used to detect the binding. The biomolecular binding can be monitored by looking at the changes in conductance. This conductance alteration of CNT FET occurs due to the charge modification of bound molecules. There are many applications of CNT FETs. Here we will discuss it in context of proteomics. The platform has been applied for detection of immunoglobulins, study of antigen and antibody reactions, detection of various cancer biomarkers and pathogen detection. One of the interesting topics to study these days is biodefense and how one can detect various pathogens which has potential of biohazard. Different type of bioterrorism attacks have caught attention, especially with anthrax and different type of SARS based biological agents. So, these nanotechniques have shown some very specific detection of various pathogens and now applied for potential application in biodefense. Let us now discuss merit and demerits of CNT FETs. This technology offers very high sensitivity with real time measurement capability. One can perform the assay in a label free environment where there is no need of adding a tag molecule. It is a cost effective and robust platform which is extremely rapid as well. At the same time, there are many demerits which are associated with CNT FET platform, including the lack of simple, flexible and well established surface modification protocols. When we talk about application of these nanotechniques as an array platform, then this particular platform is difficult to construct for the high density arrays. Let us now discuss silicon nanowire field effect transistors. The semiconductor channel is placed between the source and drain electrodes with a gate electrode on the bottom to control the conductivity of semiconductor channel. The biological receptors are attached to the surface of semiconductor channel by chemical modification to bind to the target analyte in buffer. The target receptor interaction changes the surface potential of semiconductor channel and modulates the channel conductance, and this signal is eventually measured by a detection system. The physical parameters sometimes pose constraints for sensor fabrication. Nonetheless, local FETs have overcome these limitations to a large extent, but still they have their own drawbacks. For example, the presence of metallic nanotubes and lack of well established surface modification protocols. The silicon nanowires are the building blocks of this approach. They allow tuning of sensitivity as per the requirement by controlling the type and amount of dopant in the semiconductors. Let us now discuss some of the properties of these silicon nanowires. They have very high potential for signal amplification with fast electron transfer capability. Silicon nanowires are suitable for immobilization of various biological or chemical species. They are small in size with large surface area to weight ratio. Again, the changes in conductance are measured here upon binding of charged biomolecules to their interacting partner. Let us now discuss how these silicon nanowire field effect transistors are applied for some of the proteomics based applications. As you can see in this slide, the image on the top shows silicon nanowires coated with antibody receptors. When you want to study some target proteins, and if there is any interaction of target protein with antibodies as shown in the bottom image, these target proteins will bind to antibody receptors, and a silicon nanowire will show the change in conductance. As you can see in the graph on the right hand side, conductance is plotted on the y axis with time on the x axis. From the unbound to bound state, there is change in conductance, which is measured to study biomolecular interactions. In proteomics, detection of low abundance proteins remains one of the major challenge. The high throughput proteomic techniques such as protein microarrays and various label free platforms provide good sensitivity, but when we are screening the biological fluids for detection of very low concentration biomarkers in very small sample volumes, it becomes extremely challenging. Therefore, various label free detection techniques are aiming towards detection of the low abundance proteins by using carbon nanotubes and nanowires. These studies have shown the potential of using nanotechniques for such applications where low abundance proteins can be detected with high sensitivity, and this is one of the major advantages of using these platforms. Continuing our discussion on the silicon nanowire field effect transistors, we will just go through some of their merit and demerits. This platform provides real time measurement capability with multiplexing analysis ability. It is uniform and delivers reproducible results for various biomolecule detection. It also provides high specificity. Now, discussing about the demerits, it lacks the simple, flexible and well established surface modification protocols, and that is one of its major limitations. Additionally, it is not very suitable for systematic studies. Despite some of the challenges and demerits of silicon nanowire field effect transistors, they have been applied for various types of studies in proteomics, including detection of cancer, detection of small molecules, study of small molecular interactions, detection of virus particles, different type of biosensing studies, and again similar to the viral particle detection, different type of bacterial toxin detection studies have also been performed by using this technique. So, overall, many therapeutic based studies have shown the potential of silicon nanowire field effect transistors, which can be applied for cancer biomarkers and other diseases. Let us now look at this animation to understand the principle of silicon nanowire field effect transistors more clearly. Silicon nanowire field effect transistors. Silicon nanowires can be functionalized with several chemical and biological molecules and used as sensitive detection devices. Antibodies are commonly immobilized on silicon nanowires for detection of protein antigens. No change in the conductance of the nanowire is observed in the unbound state, as you can see on the right hand panel in the graph, which is plotted within the time and conductance. Binding of target protein to the antibody is detected by change in the conductance of silicon nanowire over time, while the conductance of the unbound antibody functionalized nanowire remains unaltered. These devices offer excellent sensitivity in the picomolar to femtomolar range that and are capable of detecting molecules even at single particle level. So, in summary, today we discussed about some of the nanotechniques, including carbon nanotubes and nanowires, carbon nanotube field effect transistors and silicon nanowire field effect transistors as promising analytical tools for various applications. We will continue our discussion on few more nanotechniques such as quantum dots, gold nanoparticles, nano cages and microfluidics in our next lecture. Thank you.